NASA's Kepler Space Telescope found planets by staring at the same stars with extraordinary steadiness. Then two of its four reaction wheels failed, leaving only two when the original mission needed three. Kepler could still take pictures, but sunlight kept twisting the spacecraft away from its target. Engineers turned that nuisance into part of the solution. They rotated Kepler so solar pressure pushed almost evenly across it, then used the two surviving wheels and occasional thruster firings to hold the remaining motion. The repurposed mission was called K2. This episode asks how a telescope that had lost one axis of control learned to balance on the pressure of light. Kepler measured tiny dips in a star's brightness when a planet crossed in front of it. A wandering image would mix pointing changes with those delicate signals. The spacecraft used reaction wheels, spinning flywheels whose speed changes rotate the spacecraft in the opposite direction. Four wheels gave redundancy, while three controlled the three rotational axes. One wheel failed in 2012. A second failed in May 2013. With only two working wheels, Kepler could no longer resist torque around every axis. Thrusters could control the missing axis, but firing them constantly would disturb observations and consume limited fuel. The original continuous stare at one field of stars ended. The telescope was healthy enough to observe and powerless to stand still in the way its science required. Sunlight carries momentum. Photons striking a spacecraft create a tiny pressure. On Kepler, that pressure acted like a continuous hand pushing on one side of the vehicle. During the original mission, three reaction wheels absorbed the resulting torque. After the failures, engineers looked for orientations where the push would be balanced around the uncontrolled axis. Kepler's shape had a useful line of symmetry. If the telescope pointed near the plane of Earth's orbit, called the ecliptic, sunlight could fall across the spacecraft in a way that produced little roll disturbance. The sun stopped behaving only as the force that ruined the pointing. In the right geometry, its steady pressure became the missing support. The two surviving reaction wheels still controlled two axes. Solar balance reduced torque around the third. Thrusters corrected the remaining slow drift at intervals rather than fighting it continuously. Engineers compared the arrangement to balancing a pencil on a finger, though Kepler's balance happened through torque rather than gravity. The spacecraft also had to keep sunlight out of the telescope and maintain useful angles for power and communication. Only certain strips of sky met all those constraints. K2, therefore, could not return to Kepler's original field. It would observe a series of fields along the ecliptic, changing direction every campaign as the spacecraft followed its orbit around the Sun. The repair changed both how Kepler pointed and what part of the universe it could study. The team tested the new concept on the spacecraft, measured its pointing, adjusted control software, and learned how often thrusters needed to unload the accumulated motion. Fine pointing was not as stable as the original mission. Stars moved across detector pixels in a repeating pattern, and researchers developed ways to correct much of that motion in the data. Operational details mattered. A campaign needed an initial roll angle that minimized imbalance. Small thruster firings corrected drift about every several hours, while larger momentum management events occurred on a longer rhythm. Every firing used fuel, so the plan traded pointing quality against mission life. K2 became viable when the team could show that useful measurements survived that full cycle, from sunlight pushing the spacecraft to software removing the remaining motion from the light curves. K2 observed one field for roughly 80 days before turning to the next. That cadence was shorter than Kepler's original multi-year stare, but it opened a much wider range of targets. Scientists studied nearby stars, young star clusters, supernovae, galaxies, and objects inside our solar system, along with more exoplanets. The change also created a broad guest observer program because each campaign offered a new patch of sky. Kepler had lost the architecture needed for one famous job and gained a schedule suited to many smaller ones. This was not automatically better. Some long-period planet searches became impossible. Other time-sensitive and nearby targets became practical. A recovery often looks like that. Keep the instrument, accept a new boundary, and ask which questions fit inside it. NASA initially expected a limited number of K2 campaigns based on fuel and performance. The repurposed mission completed 19 before Kepler ran out of fuel in 2018. Across the original and K2 missions, the telescope surveyed more than 500,000 stars and left thousands of confirmed exoplanet discoveries. The number is impressive, but the visual proof of the rescue sits in a much smaller pattern: a star image drifting, a thruster nudging the spacecraft, and data analysis removing the predictable motion. K2 succeeded because each layer accepted the imperfection left by another. Solar pressure reduced the uncontrolled roll. Wheels and thrusters held the remaining motion. Software corrected residual drift. Scientists designed observations that fit the campaign length. Kepler kept working with two reaction wheels by pointing near the ecliptic and using sunlight as a balancing force. The surviving wheels controlled two axes. Solar pressure produced little torque around the third when the spacecraft used the right orientation. Thrusters corrected slow drift, and data processing handled the motion that remained. That arrangement could not restore the original mission's endless stare, so NASA built K2 around shorter campaigns and different targets. The rescue worked because the team did not demand the old telescope back. They found a new observing program inside the physics of the damaged one. Kepler lost a wheel, found a balance point, and spent 4 more years watching a different sky. The word balance can make K2 sound passive, as if engineers placed the telescope at one perfect angle and walked away. The real state moved. Solar pressure changed with geometry, stars drifted across pixels, wheels accumulated momentum, and thrusters made small corrections. Operations teams planned each campaign around those repeating changes. Data analysts then modeled the pointing pattern instead of pretending it was absent. K2 held still enough because several imperfect controls shared the burden, each on its own timescale. That active balance produced a visual identity unlike the original Kepler mission. Rather than one fixed patch near Cygnus, K2 stepped through fields around the ecliptic. Each turn put a fresh population of stars, clusters, galaxies, and solar system objects onto the detector. Damage narrowed how the spacecraft could point, yet the allowed ring around the sky created a new survey. The fix became a route.